Hello everyone and welcome back to this next video in the machine simulation series, and this is where we had left off, where we were looking at the force which is being produced by a current carrying conductor that is placed in an external magnetic field. So we had used the cross product to write an equation for this force. We already know the direction of this force from Fleming's left hand rule. We had used the vector cross product to determine a mathematical equation for the mechanical force that is produced on this current carrying conductor due to the external magnetic field, and we had defined that as this expression, which is if B is the flux density of the magnetic field and if I is the current that is flowing through the current carrying conductor, if the length of the conductor is W, it could be anything, L, W, whichever you want, then in that case the force is equal to BIW sine theta, where theta is this angle between the magnetic field and the current carrying conductor. So if the magnetic field were perpendicular to the current carrying conductor, then the force is going to be maximum. If however there was an angle theta between the magnetic field and the current carrying conductor, then one can always use the sine theta to be able to find the component of the magnetic field that is orthogonal or perpendicular to the current carrying conductor and continue to use the same formula. So we now know that this is the force, this is the equation for the force on this current carrying conductor. Now in this lecture, we'll look at how this results in a torque. So as always, before starting this lecture, if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can find on my own website, which is pythonpowerelectronics.com. So this is the homepage of the website where you can find pretty much all information related to this project. In this, if you click on this button Learn, it will take you to the list of courses which I have currently. So I have 5 online courses. The very first course is Simulating Power Electronic Circuits using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the SciPy package and the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors and transformers, all for power electronic applications. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as Python Control Package in order to analyze and design controllers for power engineering applications, with the specific example of a single phase inverter connected to a single phase grid. And the last course I have is a free course, or rather a motivational free course, which is targeted towards junior undergraduate students or even high school students, to talk about some of the challenges and opportunities available in power electronics so that these students may choose power electronics as their domain of specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy. If you click on any of these links, it will take you to the link for the course. The link for this page is provided in the description of this video, so if you're interested, please do check it out. So with this, I'll get back to the lecture. So as I already said, this is the mechanical force which is going to be exerted on a current carrying conductor in an external magnetic field. And we'd already gone through this entire process, how it happens. The reason is the current carrying conductor produces a magnetic field, and this magnetic field interacts with the external magnetic field and results in a force. This is very similar to what happens when you bring 2 magnets together. If you bring 2 magnets together, if you bring the opposite poles together, they attract. If you bring the similar poles together, they repel. And the reason is that there is a mechanical force produced due to the interaction of the 2 magnetic fields of the separate magnets. So now that we have resulted in a mechanical force, if we go back to our original diagram, that is, this is what we had discussed of a single phase induction motor. This is a simplified representation of a single phase induction motor, where we had said that all the stator windings are concentrated in these 2 slots diametrically opposite each other. In reality, there will be slots all over the stator, but for simplified explanation, this is good enough. And we had said that all the rotor bars are also concentrated diametrically opposite each other, whereas in reality they are all over the place. So with this description, we had already found that because of the magnetic field, if you go up, because of the magnetic field produced by the stator, there is a current flowing through the stator conductors, results in a magnetic field, and this magnetic field interacts with the rotor, and because the rotor bars carry a current, we all know that there is now a mechanical force. So we had said that because we can assume a direction of current for the rotor bar, so there is a current in the upper rotor bar and the opposite direction for the lower rotor bar. If we apply Fleming's left hand rule, it results in these two mechanical forces. This is the direction of mechanical force, right? And in this, for this lower bar, this is the direction of mechanical force. So it's quite obvious in this case that there is a torque which is produced, right? And this torque will cause the rotor to rotate in the counterclockwise direction. So now let us now use our knowledge of how a force is produced, the mechanical equation, and try to figure out how we can actually define this torque from these two forces. So let's go to the other diagram where we had just the current carrying conductor, and let us think of a very simplified diagram. So let's say that there is, let me just draw a little circle here. Oh, I need to actually, let me just close this. It is too complicated. And let me just delete this. So let me just draw a line from what you can say a fulcrum to some point here, right? So this is very basic high school physics. So you have here like a fulcrum. I was trying to draw it by this circle, but I'm trying to get a free line. Let me just draw it this way. Let me draw a little circle by a free line. The purpose of this circle is to show that this is a fulcrum, which means you can rotate this rod around this fulcrum, right? You can rotate this rod around this fulcrum. So what this means is, if let's say I have here a handle, so let me draw another one here. No, I'm drawing a curve, sorry. Let me come back here and draw with freehand a handle. So here we have a handle. We have a handle on one side and we have a fulcrum on the other side. So if we exert a force, like we grab this handle, we can move it around. So similar to what you would do in a playground, right? You just have these things which you can just run around them. Children can run around them. Similar concept. So if you exert a force on this side, this will rotate. Now the question is, in which direction should be the force? So let's say, for example, let me again draw a line, and let's say this force was in this direction. I hate it when it just joins it. Okay, let it join it, I don't care. Right? So I have now drawn a force. Let me just use the free hand to draw an arrow. So this is the direction of the force, right? So I am pushing this handle in this direction. Now, if I push this handle in this direction, this will move, right? Because this is a fulcrum. And being a fulcrum, this can sort of pivot around this fulcrum. Now the question is, what part of the force causes it to rotate? Now, here again, we can, for this particular rod, we can have two different components. So for example, let me take this and let me draw one which is in the same direction. So I'm just going to extend it, and another one which is perpendicular to it. Okay, this is roughly perpendicular. Yeah, well, it looks like that anyway. It's okay. So I have a rod and I have now drawn two components. Actually, let me escape it. I have a rod and I'm drawing two components of the rod. One is along the rod and the other is perpendicular to the rod. This force can be decomposed into two components. That is, this force can be decomposed into a component along the rod and perpendicular to the rod. Right? So, let me draw that also. Let me take this line here and draw it. It just chooses to join it, so I need to stop a little before. And here I'm going to draw another one. This is perpendicular to the rod. Again, I can't go too close because it decides to join it. Okay, I think this is good enough. So I have now drawn two components. Let me again use the freehand to draw arrows. So I have now, I don't know why I joined it here. Anyway, let it be. So there is the actual force here. There are two components of this force. Basically, all I'm doing is I'm just decomposing this into two components. So if you define this angle as some angle, theta or phi or whatever, then in that case, this force, if this force is F, this component of the force is F cos phi, and this component of the force is F sin phi. Alright, now the component of the force, that is F cos phi, which is along the rod, is not going to cause this rod to rotate. Why? Because it is along the rod. Right? If you push it along the rod, if you really exert a huge amount of force, you might end up breaking the rod. But you won't cause it to really move. What will cause it to move is this component, which is perpendicular to the rod. Why? Because there's a fulcrum and it can rotate. So this, if we draw an arc, I'm still on freehand, so let me just draw an arc. It's not going to look very nice. Actually, no, it's not on freehand. Okay, I think now I'm on freehand. If I draw an arc, okay, it looks terrible. But this is an arc. So this is an arc where this rod can rotate. Looks absolutely terrible, but use your imagination. If this was a fulcrum, it can rotate in a circle around it. Which means that if that is possible, this rod, and if there exists a component perpendicular to the rod, this component, if a force acts along this component, it is going to be tangential to this circle. Right? You remember this is a tangent. If I draw a component along the rod, this is a radius. The perpendicular component is the tangent. So if this force is along the tangent, this has maximum impact on this rod and will cause it to rotate. So this will cause this to rotate in this direction. I don't know why I joined it like this, but anyway, the idea is it's going to cause it to rotate in this direction, which is the clockwise direction. So if you look here, once again, we have said that there is now going to be a force on a mechanical force on a current carrying conductor which is placed on an external field. And we have also said that we can calculate this mechanical force using the flux density, the current flowing through the conductor, the length of the conductor, and the angle between the flux lines of flux, or rather lines of magnetic force and the current carrying conductor. Now the next question is, what is the nature of force? Right? So we have said that there can be a force, right? So force will act. If there is a conductor and a force is acting on the conductor, what will cause this force to really move is the component which is along the tangent to this circle of movement, right? That is what matters. So we now have two equations. Let me go and write that as well. So we can say that if there is this force, and this force is, I'll just put it as force actual, because this is the actual force that matters. This force multiplied by sine of phi, where phi, oh my god, undo that, yeah. Phi is the angle, phi is this angle between the force and the rod, right? So this angle phi is the angle between the force and the rod. If we define this angle, then in that case, our actual force which causes it to rotate is going to be F sine phi. So we have two angles. We have an angle between the magnetic field and the current carrying conductor. We have an angle between the mechanical force and the actual, radius of rotation, right? So we have these two forces. Now that we have these two forces, we can now use this on our machine to figure out what is the actual force which is going to cause this machine to rotate, right? And this we can do using this other diagram, which is namely this one, right? We have already this diagram where we have used Fleming's left-hand rule to determine the direction of mechanical force, and we have also figured out that there will be a torque produced because of it, which will cause it to rotate. But now the next question is, what is the actual force acting on this rotor conductor which is going to cause it to rotate? Because remember, not all the force may cause it to rotate, right? In this case of an induction motor, for a special case and specially designed, one will find that a vast amount of the mechanical force is indeed going to cause it to rotate. There is only a very, very small component of mechanical force which is largely wasted and results in vibration. And we'll talk about that very soon in the next lecture. But this was the idea behind this lecture, is to talk about, one, the direction of mechanical force which causes a machine to rotate, and to actually decompose any mechanical force into different components and determine which component it is that actually causes a machine to rotate. So I will continue in the next lecture where we will use these equations on this machine, this specific simplified machine, to come up with some rudimentary equations for the mechanical torque, right? Which is largely the torque which is produced and causes this machine to rotate. Again, a quick word, we do not use this method to calculate the electrical torque, right? And I'll talk about that also very soon. The reason I want to tell you is this description shows how we can use basic physics to determine how an electrical motor works. That is the idea behind all this. And we can even come up with some basic equations to actually describe mathematically what is actually going on. So this is not just science fiction. This can all be written down mathematically. But for our purposes, we'll use another method, and I'll talk about that in a few lectures once we complete this discussion. So as before, if you have any doubts, please do either send me an email or message me on social media or put a comment, whichever is your preference. Otherwise, I will see you next week where we will continue and figure out how this machine will rotate. Thank you so much for listening, and goodbye for now.